Hi there, welcome to this Elkchemist A-level chemistry video focusing on Born-Haber cycles. So, a Born-Haber cycle is a thermochemical cycle usually designed to calculate a certain missing enthalpy change. Most commonly, the enthalpy change will be the enthalpy change of lattice formation, otherwise known as lattice enthalpy, and that is the enthalpy change for the formation of 1 mole of an ionic compound. Now, that enthalpy change cannot be calculated directly, so it must be calculated indirectly using a Born-Haber cycle. The way this works is the other enthalpy changes shown in the cycle represent the enthalpy changes that will go into the formation of 1 mole of that ionic compound and can be used to calculate our missing enthalpy change by applying something called Hess's Law. So Hess's Law states that the enthalpy change in a chemical reaction will be the same independent of the route taken. Let me illustrate that point with our Born-Haber cycle. Imagine our objective is to form 1 mole of sodium chloride solid. Now, I've got two different routes I could take to do that on this cycle. There is a direct route, which is known as the enthalpy change of formation, taking elements in their standard states, sodium and chlorine, and reacting together to form sodium chloride. And that is our direct route 1, with a certain exothermic enthalpy change. Now I could also take a much more long-winded indirect route, going through all these various enthalpy changes I'll highlight later, but ultimately taking route 2 from this point all the way around with all these various enthalpy changes still results in the formation of 1 mole of sodium chloride. And let's call this circular route around here route 2. Hess Law states that the enthalpy change of route 1 will be equal to the enthalpy change of route 2. And therefore, if I were to go full cycle and take away route 1 from route 2, I'd end up with an enthalpy value of 0 kilojoules per mole, as route 1 has equal energy to route 2. So, what's important about that is that we can manipulate Hess's law to calculate any missing enthalpy change on this diagram, and that's incredibly powerful. So I'm going to take you guys through some definitions of what each of these enthalpy changes actually are, because they're important for the A-level syllabus. Then I'll take you through how to use a Born-Haber cycle to calculate our missing enthalpy change of lattice formation, or as I'll call it from now on, lattice enthalpy, and how that calculation works. So, delta H theta F is the standard enthalpy of formation. It's the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions, which is what the theta symbol is telling us. That's 298 Kelvin and 1 atmospheric pressure, with both reactants and products in their standard state. So elements in their standard states going to a compound in its standard state as well, as it's found at room temperature and pressure. Both of these enthalpy changes, respectively for sodium and chlorine, are delta H theta AT. The standard enthalpy change of atomization of an element is the enthalpy change for the formation of 1 mole of gaseous atoms of that element from the element in its standard state. So this is atomizing sodium and atomizing chlorine, which I'll go through shortly. Delta H theta 1 IE stands for the first ionization energy of sodium in this particular example. And it's the enthalpy change for the removal of 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous monopositive or 1+ ions. The absolute polar opposite or flip side of the coin of that definition is delta H theta 1 EA, which is the first electron affinity for an element. In this case, it will be chlorine. And it's the enthalpy change for the addition of 1 mole of electrons to 1 mole of gaseous atoms to form 1 mole of gaseous mononegative or 1- ions. Now, once you have your ions in the gaseous state, you can then turn those into a giant ionic lattice or an ionic compound, and that involves delta H theta LE, or the enthalpy change of lattice formation for an ionic compound is the enthalpy change when 1 mole of that ionic compound is formed from its constituent gaseous ions. So the two main tasks you'll have for a Born-Haber question or problem will be writing the enthalpy change equations on these lines that represent the processes taking place. So our bottom line I've labelled ionic solid. That's where we're going to write the formula of our 1 mole of ionic compound. In this case, our objective is to make sodium chloride. That's a 1-to-1 ratio formula because sodium ions are +1 and chloride ions are -1 ions, and so to create a stable ionic compound with those charges balancing out, I need a 1-to-1 ratio of sodium ions to chloride ions, Na plus Cl minus. Next, I want to place the elements in their standard states on this line to show how this enthalpy of formation occurred. So sodium in its standard state is going to be a solid because it's a metal, and chlorine in its standard state at room temperature and pressure is a green gas, so I'll write G next to chlorine's formula. Now the question is, why have I written Na plus a half Cl2? Right? Why haven't I just written Na plus Cl2? What's the requirement for that half value here? Well, it's because we have to make sure we are creating the correct formula for our compound, which is NaCl, a 1-to-1 ratio of sodium ions to chloride ions. And secondly, it's down to the nature of the definition of enthalpy of atomization. Enthalpy of atomization states is the enthalpy change for the formation of 1 mole of gaseous atoms from elements in their standard state. Now, the element in its standard state for chlorine is Cl2. Okay, so if I were to break 1 mole of chlorine molecules to release gaseous atoms by breaking the covalent bond, freeing up those atoms, well, 1 mole of chlorine molecules contains 2 moles of chlorine atoms bonded together. And when I break the covalent bond, I will release 2 moles of gaseous chlorine atoms. That's 2 times the enthalpy of atomization. And it's more than I require in this particular Born-Haber cycle, because I'm trying to produce NaCl, which is a 1-to-1 ratio of sodium to chlorine. I don't need 2 moles of chlorine atoms to produce an NaCl formula. I only need 1 mole of chloride ions to bond with 1 mole of sodium ions to make this NaCl formula. So therefore I bring a half Cl2 because that would only bring half the number of chlorine atoms from breaking down 1 mole of chlorine atoms. Breaking down half a mole of chlorine atoms will release 1 mole of gaseous chlorine atoms and hence provide the right amount for this scenario. To the enthalpy of atomization of sodium, i.e. turning sodium from its standard state solid into the gaseous state. So all I do is I change the symbol S to G. The chlorine has not yet been affected. I haven't atomized the chlorine yet, so it's still half a mole of chlorine molecules until I get to the next atomization stage. Then we come to the atomization of chlorine, atomizing half a mole of chlorine molecules to release 1 mole of chlorine atoms in the gaseous state, and that would be represented by Nag and now Clg for that 1 mole of gaseous chlorine atoms. Now we've come to the first ionization energy for sodium atoms, converting 1 mole of sodium atoms in the gaseous state into 1 mole of sodium ions, monopositive +1 ions in the gaseous state. So I take Nag and it becomes Na plus G, Na plus being gaseous sodium. The chlorines haven't been ionized yet, but there's the mole of electrons released from the mole of sodium ions in that process. They're still floating around, ready to be picked up by the chlorine in this next stage. As I said, the next step is the first electron affinity, the enthalpy change for the formation of 1 mole of mononegative ions from chlorine atoms in the gaseous state. So I'm turning my chlorine atoms into chloride -1 ions by gaining that mole of electrons. So all I write is Na plus gas and now Cl minus in the gaseous state. That's because they've picked up that mole of electrons onto the chlorine atoms, making them -1 ions in the process. And those are all the various stages outlined on our Born-Haber cycle. And you must write these on the lines to show the process taking place. The next step is to put some values on and see our calculation. So at this point, you'll be given the enthalpy change data for the various enthalpy changes taking place, probably in a table. And at this point, I can highlight that the direction of arrows shown actually has some significance and meaning. If the arrow is going down, it's emphasizing that enthalpy change is exothermic in nature, it's giving out heat energy to its surroundings, and it will be a negative enthalpy change. On the other hand, if the arrow is ascending, it means it's an endothermic process. It's taking in heat energy from its surroundings, and the enthalpy change value will be positive. Here I've now added the enthalpy change values in kilojoules per mole for the various enthalpy changes shown. I'm going to tell you how to apply Hess's law to find this missing enthalpy value we're looking for, the enthalpy of lattice formation. So if you think back, Hess's law stated that the enthalpy change of a chemical reaction would be the same, independent of the route taken. Now I'm looking for the lattice enthalpy, but I don't know what it is because I can't work it out directly. But maybe I can take an indirect route to find it. The enthalpy change of route 2, which I've drawn here in green, gets me to the same endpoint of forming sodium chloride. So if I work out the total enthalpy change of route 2, it'll be the same as that for route 1 according to Hess's law. And that's exactly what we're going to do. I'm going to share with you my ultimate top trick for never getting a Hess or Born-Haber cycle question wrong. Whichever arrow you're looking for in the question, find the tail of the arrow in question and circle it and write the word start. That will be your starting point. Then put a square around the head of that same arrow and write the word finish. And that will be your finishing point. And then you're going to go around the cycle from start, ending at the finishing point in this direction, for example, for this particular Hess cycle, and it will give you the missing enthalpy for this arrow. I'm going to take you around the cycle. We're going against the direction of the first electron affinity. So we're doing the opposite of that enthalpy change, minus 349 kilojoules per mole. We're going against the direction of the arrow for the first ionization energy. So we're doing the opposite of that process energetically, minus 496. We're going against the direction of the atomization of chlorine arrow. So we're doing the opposite energetics of that particular reaction, minus 122. We're going against the direction of the enthalpy of atomization arrow for sodium. So we're doing the opposite energetics of that enthalpy change, minus 107 kilojoules per mole. And finally, the arrow we're finishing with is going in the same direction as the enthalpy change of formation. So effectively we're doing the same process energetically, which means we're going to just add or just do minus 411 kilojoules per mole at the end. And our overall total will give us our missing enthalpy change of lattice formation, or lattice enthalpy. So I've also included a quick summary of that calculation I did with symbols and with values as well. Remember, if the direction of arrow for our route was the opposite direction to the original enthalpy change, it's as if we're doing the opposite energetics. So the first electron affinity is an exothermic process, but our route is actually taking an upwards direction and therefore is an endothermic process. So it's plus 349, or in other words, minus 349. So that's why I've included these minus symbols and plus symbols to emphasize if we were going against an arrow direction, that would be a minus symbol, or with an enthalpy change direction, which would be a plus symbol. So to summarize, we're doing minus 349 because we went against the direction there, minus plus 496 because we went against the direction there, minus plus 122 went against the direction there, minus plus 107 went against the direction there, and finally plus minus 411 because we went with the enthalpy change of formation arrow there, the same energetics effectively. And if you do the sum of this calculation, you'll come out with minus 787 kilojoules per mole. That is the missing enthalpy change of lattice formation, or lattice enthalpy, for the formation of sodium chloride. That is our value here. So we've solved the problem. Now, quite legitimately, students can often worry that maybe that answer isn't right. It's just a random number for that energy change, and it's very easy to make a calculation error and get it wrong. So is there a way we can check that answer to see if it's correct? Well, luckily, Hess Law has one more little trick up its sleeve that allows us to do that. I'll talk you through that now. If Hess's law holds true, then if I go full circle from my starting point, effectively what I'm doing there is taking route 2 and then taking away from route 2, because I'm going against this arrow, route 1. And if root 2 has the same enthalpy change as root 1, then if I take away the value for root 1 from the value for root 2, well, then I should end up at absolutely 0 because they have the same enthalpy change. So if I do that, go full cycle and get 0, I know definitively that my root 1 value must be right, because if it wasn't, then it isn't agreeing with Hess Law, and therefore I must have made a mistake. Let's just see what happens on a calculator when I do that. Right then, here we go. Hopefully a little hand should appear and take you round the cycle as I work through this. So it's minus 349, because we're going against that arrow direction. Then it's minus the plus 496. Then it's minus the plus 122. Then it's minus the plus 107. Then it's plus the minus 411, because we're going with that arrow direction. And then finally we're going to go against the arrow direction for the whole of root 1. So it's therefore minus 787. And now drum roll please. The answer should be 0. And if I press equals, the answer is 0. So Hess Law does hold true, and that's our proof that we did make a mistake and we got our enthalpy change for lattice formation or lattice enthalpy spot on. That's ace, guys. Thanks so much for listening to the end. Now, actually, this is part of a series of videos on Born-Haber cycles. This was my intro video, but I'm now going to start covering more complex Born-Haber cycles. So do look out for any cards that appear in this video, which will take you to the next one in the series, and there'll be hopefully some links at the end of the video as well. As always, thanks so much for listening, and if you found this video useful, please think about giving it a like, maybe think about subscribing to the channel, maybe even ringing the bell to keep notified of our latest content. Now move on to A-level videos. Maybe even think about sharing this video with friends who need some help in chemistry. I'm trying to do this on a weekly basis, and I just love talking chemistry. So thanks very much, and I'll see you in the next video. Take care. Bye now.